Okay, so remember we have our mass on a spring, okay, and we went through the Newton's second law, F equal ma, okay. We wrote the equation of motion, and then the solution of that was a sine or a cosine. Okay, so this thing oscillates back and forth between plus or minus theta max, right? And the omega, right, that's the angular frequency. Okay, and remember, since it only oscillates at one frequency, okay, it's called simple harmonic motion. Okay, we showed a video where we had a system of 3 masses, 4 springs. The system oscillated in 3 different modes or 3 different frequencies. Okay, so again, this is just our simple harmonic oscillator. 1 mass, 1 spring. Okay, so let's say this thing's pulled back, okay, at time equals 0, and let's say it's pulled back to 5 centimeters and released at time equals 0, and I want to draw a graph of that. Okay, so if it's released at x max, okay, then it starts up high, so that'd be a cosine. Okay, and the amplitude is 5 centimeters, no big deal, right? But let's say maybe you bought your calculator on sale and it didn't have a cosine button. It only had a sine button, and you needed to write that as a sine. Okay, well, you'd have to include a phase shift. Okay, so that's the curve that describes the mass being released at x max at time equals 0. Okay, so this curve right here I redrew there. Okay, that's the black curve. Okay, so it starts at the top. That'd be a cosine. All right, but it's been shifted. Okay, so you want to write that curve, that function, as a sine. Okay, well, a sine looks like this. Okay, that's the purple curve. Okay, so the original curve that we want to write as a sine function, well, we have to take this purple sine curve and shift it over to the left. Okay, so that's the phase shift we have to figure out. All right, now how much is it shifted over? Well, from trig class, you know that it's shifted over by pi over 2. Okay, but is it shifted over plus pi over 2 or minus pi over 2? Okay, now we got to go back to algebra. All right, so let's say I just have a graph of y equal x. Okay, regular xy plane goes right through the origin right there. Okay, now let's say if I draw this green line, okay, that one right there, okay, and it passes through x equals 2, all right, I claim that that's written as y equal x minus 2. Now, how do I know that? Okay, how do I know that that's y equal x minus 2? Well, when I put in x equal 2 right there, okay, I get 2 minus 2 is 0. So sure enough, at that point, okay, when x is 2, y is 0. Okay? So that says that this blue curve, if it's shifted over to the right, okay, then that's written as x minus 2. Okay, so that could be written as right here, x minus phi. Okay, where phi, this says phi is a positive number. So if it's x minus a number, okay, that minus phase shift is something that's been shifted over to the right. Okay, this line over here, okay, goes through x equals minus 2. So I claim that that's written as y equal x plus 2. Okay, how do we know that? Well, if I stick in x is equal to minus 2 right there, okay, if I stick in x is minus 2, so minus 2 plus 2 is 0, because that point right there is minus 2 comma 0. Okay, so sure enough, if I take this blue curve here and I shift it over to the left, okay, then that's written as a positive phase shift. So that's written as y equal x plus phi, where phi is a positive number. Okay, so that's how we remember the direction of the phase shifts. Okay, x minus 2 shifted to the right, x plus 2 shifted to the left. Okay, so we know that this sine curve, okay, that sine curve, okay, it's easier to look at the peak. Okay, that sine curve is shifted over to the left by pi over 2. Okay, shifted over to the left. That's a positive phase shift. So then we would write that as, okay, that phase shift is plus pi over 2. Okay, so that's why I wrote it right there. Right, and right, you can even see if I put in time equals 0. Okay, at time equals 0, sine of pi over 2 is 1, and sure enough, okay, that's a high point at 1. All right. Now, let's say the system's already oscillating. Okay, so it's Okay, it's already oscillating, and someone walks through the door and starts their timer at time equals 0, right when the block is at the equilibrium point, and head it to the right. Okay, so that curve, okay, that curve would be written like this. So it starts at 0, and then it goes to x max. Okay, so that's a sine. And I have the amplitude was 5 centimeters. Okay, so I could write that as a sine. All right, but let's say you need to write it as a cosine. Okay, well, the cosine is the purple curve, right? Starts out high, all right? But our curve starts out at 0, all right? So we wanna write that as a cosine, okay, a shifted cosine. So this cosine, okay, the top of that cosine has been shifted over. I didn't draw the rest of it, but the top of that cosine has been shifted over, okay, by how much? By pi over 2. So it's shifted over to the right. Okay, and we saw that if things are shifted over to the right, you write it as x minus something, okay, or the variable minus something. So then that phase shift is minus pi over 2. Okay, so that's how that's how we could write the function. Okay, if we needed to write it as a cosine, the phase shifted cosine. So that's why it doesn't matter if you use cosine or sine. If you buy a calculator, it doesn't have a sine button, you can use cosine. Okay. Okay, and just to make sure, if I put in time equals 0 right there, okay, time equals 0, 0 minus pi over 2, okay, remember that pi over 2 minus pi over 2 is down here, okay, so cosine of minus pi over 2 is 0, and sure enough, at time equals 0, that's where the object is. So we found the position function for the mass on a spring, okay, and then we wanted to find the velocity and the acceleration. Okay, so here I have a mass and spring, okay, released at time equals 0 at x max, okay, so I just drew one whole cycle. So from where you start, that's one cycle, that's one period, okay. So I labeled the places A, B, C, D, and E, all right. Okay, so I want to plot position, velocity, and acceleration versus time for a period, all right. Now, this picture, it would also work for this picture here. Okay, so you would release it up here at y max, and it would come back up, okay, for one cycle. Okay, so we already know the position function, all right, and you know that to find the velocity is the time rate of change of position. Okay, so I take the derivative of position with respect to time, I get an omega on the outside, okay, derivative of cosine is minus sine, okay, so this stuff in front, okay, omega x max, it's in front, so it's the amplitude, okay? So if that's velocity, then the amplitude is called velocity max, or V max, okay? To make it even more confusing, next semester, that V is going to be voltage, okay? And that thing is going to be maximum voltage, okay, when you're doing alternating circuits, okay? Okay, all right, so this V max, all right, is omega x max, all right? Now, where does that come from? Let's go back down. I'm going to go down here. Okay, so here's our mass in a spring, all right, going back and forth, all right, and remember, we try to make the connection between circular motion and simple harmonic motion, okay, so here I have a ball going around a circle, okay, it's going around a circle at constant speed, okay, so the speed of the ball, okay, let's say at the rim of a bike, or the speed of the ball is r omega, all right, and maybe I have a light up here, okay, shining a shadow, or shining a light on the ball, and the shadow's down here on the floor, okay, and the shadow's going back and forth, okay, as the ball goes around, okay, that shadow is going back and forth, okay. So if I look at the shadow, okay, the shadow is in simple harmonic motion, just like the block on a spring, okay. Now, as the shadow goes back and forth, okay, it's at rest at the endpoints, just like the block is at rest at the endpoints, okay, at the amplitudes, all right? So the maximum speed of the shadow, okay, so the maximum speed of the shadow, okay, here's the shadow going back and forth, all right? Well, where did the shadow get its speed from? Well, it got it from the ball. Well, the ball's going at constant speed, okay? Constant speed of r omega, but the shadow's not going at constant speed. So the fastest that the shadow is going to be going is when the ball is at the bottom, moving that way, or at the top, moving that way. okay, and that'll be the shadow right there moving left or right. Okay, so the maximum speed of the shadow just comes from that constant speed of the ball, which is r omega, okay, which is the same as the maximum speed of the block, because the block's doing the same thing as the shadow. So what plays the role of the radius? Okay, if I project that up, okay, what plays the role of the radius? Well, the amplitude. Okay, so I'm going to replace the r with x max. Okay, so I'm making a connection between what the shadow's doing, okay, which is from the ball go around in a circle, to the block. So that's another way to realize that V max for the block is omega x max. Okay. Okay. All right. So let's see what the graphs of these look like. Okay. So we know that the position is a cosine. Okay. So I graphed. I put points here A, B, C, D, and E. All right. Well, velocity. Okay. Remember, velocity is the slope of the tangent line of position. So I go to anywhere on the position graph, okay, and I put the slope of the tangent line. What can you tell me about the slope of the tangent line at that point? It's negative. Well, what does the slope of the tangent line mean? It's the velocity. So sure enough, the velocity, right, is a negative number down there, okay? So as it goes from A to B, okay, so as the block moves from A to B, what can you tell me about the slope? Well, the slope is increasing in magnitude. So the velocity is getting bigger and bigger in magnitude, right? So V is increasing, okay? All right, and all the way to C, the slope of this tangent line, okay, the slope of those tangent lines are still negative. So velocity is still negative, right? Velocity is headed to the left, okay? But what can you tell me about the slope, okay, as I go from B to C? Okay, the slope is becoming smaller in magnitude. So sure enough, the velocity is getting smaller, okay? And where is the slope, okay, between A and C? Okay, between A and C, where is the slope the biggest? Okay, right at B, right at the inflection point. Okay, not drawn too well. Okay, so right at the inflection point. So the biggest slope means that's where the velocity is the biggest, and sure enough, at point B, okay, when it passes through the middle point, that's where the velocity is the biggest. At point C, what's the slope of the tangent line at point C? Slope is 0. What does the slope represent? Represents the velocity. So sure enough, at point C, velocity is 0. Okay, so at the end points, the velocity is 0. Okay, now what happens when I pass from C, or from the left side of C to the right side of C? Okay, well, the slope is now positive. Okay, but the slope, okay, slope of the tangent line, okay, is the velocity. So the velocity just changed to positive numbers. Those are positive numbers. So that means it now has turned around and it's headed to the right. Okay, and those slopes stay positive, okay, all the way to E. Means the block is headed still to the right. Okay, where is the slope the biggest from C to E? Slope is the biggest right at the inflection point. Okay, ooh, that one's drawn pretty bad. Okay, so right at the inflection point, there's where the slope is the biggest. So sure enough, that's where the velocity is the biggest, right there at point D. Okay, so the velocity is the biggest when it passes through the equilibrium position at B, and again the equilibrium position at D. Okay, what happens to the slope of the tangent line on the other side of D? It gets smaller and smaller. Eventually you get a horizontal tangent that says the velocity is now 0. So sure enough, velocity is 0 at the endpoints. If I look at the acceleration, okay, if I look at the velocity graph, how is acceleration represented on the velocity graph? Okay, we go to any point, okay, you go to any point on the velocity graph, right there, and the slope of the tangent line gives you the acceleration. So what can I say about the slope of the tangent line right there? Slope's negative. That means the acceleration, okay, would be a negative number. So acceleration has to be a negative number down here, and it is. Okay, so the acceleration is negative from A to B because those slopes are negative. So sure enough, from A to B, okay, your acceleration is negative, right? And if both A and V are negative, that means this thing is speeding up, right? The speed is increasing. Okay, now at B, if I take a tangent line for the velocity at B, slope of the tangent line 0, that says the acceleration 0. Right there, the acceleration 0. So whenever it passes through the equilibrium position, that's when the spring is relaxed, okay? And if there's no net force on the spring, okay, that means the acceleration has to be 0, okay? And then once it passes from B to C, okay, it passes from B to C, the slope of the tangent line for velocity is now positive, but the slope of the tangent line is the acceleration. Now the acceleration is a positive number, okay? So as soon as it changes over, it passes B, the acceleration changes direction, okay? Acceleration is now a positive number, all right? Now, A and V point in the opposite direction. That means it's guaranteed to be slowing down. So the speed is now decreasing. It's putting on the brakes, right? Putting on the brakes so the velocity stops at C, okay? Now, where is the slope of the tangent line for velocity the biggest around here? At C, okay? At the inflection point. So the slope of the tangent line is the biggest. That means the acceleration is the biggest at point C, and it's positive. So you have the biggest positive acceleration at point C. Okay, so over here at C, that's where you have A max. It's a positive number, plus A max. Okay, and then once I go past D, okay, from C to D on the velocity graph, slope is still positive, so acceleration is still positive, but again, it's getting smaller. So acceleration is still positive, head it to the right. Okay, so that means V is increasing to the right from C to D. Slope of the tangent line at D is 0. That means the acceleration at D is 0. Okay, so we know that. Acceleration at D is 0. That's the relaxed point. And as soon as I go past point D, now the slope of my tangent line is negative. That means the acceleration is negative. And sure enough, here my acceleration is a negative number. Okay, so that means the acceleration changes direction, and now your speed is decreasing because it's putting on the brakes. And then where is the slope between D and E for velocity? Where is the slope the biggest? Right there at E. Okay, and the slope is the acceleration. So that means and that's a negative slope. So that means that's where you have negative maximum acceleration. Okay, so at point E, right there. So at point E, you have minus A max. Okay, so the weird thing is the velocity is 0 on the endpoints, which makes sense. It's going back and forth and stopping. But when it turns around, okay, and then it turns around, the accelerations are maximum at the endpoints, okay, but it's plus A max on the left and minus A max on the right because the direction is the direction that the change of velocity occurs in. Okay. All right. So anyway, we had the velocity here. Just take two derivatives. Just take one derivative, right? And that gives you the acceleration. So you get another omega on the outside. So I have omega squared. Derivative sign is cosine. Okay. This stuff in front, that's the amplitude. Okay, not the minus sign, but just this stuff in front, that's the amplitude. Okay. So that's now called A max. Okay. So A max is omega squared x max. Okay. So if I go back to the wheel, okay, to look at A max, all right, here's the wheel. Okay. So remember, the ball is going around in a circle at constant speed. Okay. So it has a centripetal acceleration from the circular motion chapter. Centripetal acceleration of the ball is v squared over r. Okay. And remember, the linear speed of the ball is r omega. Okay, so I have an r squared on the top, r on the bottom, so one of the r's cancel. So that's the centripetal acceleration right there of the ball, okay, or at any point, right, toward the center. As the ball goes around, okay, the centripetal acceleration is constant in magnitude, but it's always changing direction, all right? But if I look at the shadow, okay, the shadow gets its acceleration from the ball going around the circle. So the maximum acceleration of the shadow, okay, is that constant acceleration, centripetal acceleration of the ball, which is r omega squared, okay, which is the same as the maximum acceleration of the block, because the block is doing the same thing the shadow is. So what plays the role of r? X max, right? So we said it before. So the radius, okay, projected up there is the same as the amplitude x max, all right? So that's why that's another way you can think of where that amplitude comes from. Okay, so here I just drew the summary Okay, so the velocity is 0 on the endpoints. The acceleration is maximum in magnitude at the endpoints. The velocity is a maximum at the center. Okay, remember the acceleration is 0 at the center. Okay, and the reason is because the net force is 0, right? That's the relaxed position of the spring. Okay, so as this thing goes back and forth, okay, you have all potential at the end. You have all kinetic in the middle because the spring is relaxed at the middle, and then all potential at the end, okay? And then somewhere in between, okay, maybe you have maybe a 50-50, half potential, half kinetic, all right? So we want to know, where is the kinetic energy equal to the potential energy? Okay, we'll look at two different ways to do this, all right? So first we have to look at the energy of the system. Okay, we haven't looked at the energy for a simple harmonic oscillator. Okay, so here again, I'm just showing one cycle, starts at A, okay, does one period, one cycle, all right? And I'm going to write the kinetic and the potential. So I'm starting with the position, okay? Take the derivative to get the velocity, all right? So the kinetic energy is 1/2 mv squared. So 1/2 m times that stuff squared. So I squared that, okay? And then again, I show in my picture that when I let it go, all the energy's potential stored in the spring. When it passes equilibrium, springs relax, so all the energy's kinetic. At the end point here, it's at rest, so the kinetic energy is 0, all the energy is potential, okay? So it oscillates back and forth between all potential, all kinetic, all potential, all kinetic, and so on, okay? So eventually we want to find where it's a 50-50 split. Okay, so I wrote my kinetic energy, 1/2 mv squared, all right? So I just rewrote that right there, okay? And I just kept the 1/2 on the outside, right? And then remember what I did from our treatment of simple harmonic motion, okay? All right, omega squared is k over m. So if I solve this for m omega squared, okay, because here I have, here I have m omega squared right there. Okay, so m omega squared is k. Okay, so that stuff right there, that's the spring function k. So I have m omega squared, I put in a k. Okay, so that's my kinetic energy. Potential energy, okay, remember potential energy is 1/2 k x squared, okay? Well, that x is this x, okay? So whatever the value of x, okay, that's potential energy, right? So I wrote 1/2 k x squared, okay? And that whole thing is my x, all right? So now I have the potential and I have the kinetic. Okay, so if I graph them, if I graph the potential and the kinetic, all right, so here's the hard part. So let me look at the kinetic energy. Okay, kinetic energy goes as sine squared. Well, the black line here, okay, is y equals sine x, all right? So it goes from a maximum 1 to a minimum minus 1 and so on, all right? So what does it look like if I square it? Okay, well, when I square it, okay, it kind of has that form. Woo. Okay, it's above, right? They're not cusps, right? Couldn't be a cusp because you couldn't take a derivative, right? It wouldn't be differentiable, and you know you could take a derivative of sine squared. So it kind of has this form. Okay, so here is the kinetic energy. Okay, so time equals 0, starts at 0, and then it goes, what I did here is, if I square that 1, it stays a 1. If I square the 0, it stays a 0. If I square the minus 1, it jumps up here to a 1. If I square the 0, it stays a 0. Okay, so it goes my 0, there's my 1, there's my 0, there's my minus 1. Okay, so there's my 0, 0, my 1, my 1, my 0, 0, my 1, 1, and then my 0 there. Okay, so from A to E, that's one whole period, okay, for the kinetic energy, all right? And then I did the same thing for potential energy, okay? Potential energy goes as a cosine squared, okay? So that starts high, so the 1s go there, the 0s go there, that's the minus 1, okay? That's the 0, right? So that's the 1, 0, minus 1, 0, back to 1, okay? So this whole graph is one period for the motion, all right, from A all the way to E. Okay, so if I look at that, this says that when the kinetic energy is minimum, 0, potential energy is the max, okay? And then a quarter cycle later, okay, quarter cycle later, now the potential energy is a min and the kinetic energy is a max, okay? So the kinetic and potential energy are out of step, or they're out of phase by a quarter cycle, okay? So quarter cycle will be from A to B, okay? A to B is a quarter cycle, and so on, okay? So from trig class, that interval there, that's pi over 2, okay? So the book might say the kinetic and potential are out of phase by pi over 2, okay, which is a quarter cycle, or okay? So the total mechanical energy, capital E, is always kinetic plus potential. So if I add kinetic plus potential, okay, add those two up, I can factor out 1/2 kx max squared. And if I factor out 1/2 kx max squared, I have sine squared plus cosine squared, which is 1, okay? And I wind up with that. So the total energy is 1/2 kx max squared, okay? Well, k is the spring constant. That's a constant, hence its name. And x max is a constant. It's whatever amplitude you let it go. So the total energy remains constant, okay? Assuming there's no friction, okay? So remember, what this means is, if I go back on my picture, okay, all the energy is potential, all kinetic, all potential, and so on, okay? All right? So right when I start, all the energy is potential, 1/2 kx max squared, all right? So you have to be careful, because if they give you some value of x right there, okay, and they ask you to find the energy, all right, okay, well, that's not that x, all right, but it doesn't matter, because whatever amplitude it was released at, that x max, you know. So if the total energy, the initial energy is 5 joules, the energy anywhere at any point is 5 joules. So if you know the amplitude, then you always know the total energy, okay? So let's get back to finding when is the kinetic equal to the potential, okay? So I'm going to set this kinetic equal to that potential, okay? So here's my kinetic, goes as sine squared. There's my potential, goes as cosine squared, okay? So I'm trying to find where and when, all right? So the half k's cancel, the x maxes cancel, okay? And I'm left with sine squared equals cosine squared. Okay, and we know from trig class that sine squared equals cosine squared at the 45s, right, at plus or minus pi over 4. Okay, so then what I'm going to do is I'm going to take omega t, and I'm going to put it into my position. Okay, where's my position function, right? There's my position function. So I'm going to put in omega t is pi over 4. Okay, so if I put in omega t is pi over 4, okay, you know the cosine of pi over 4 is 1 over the square root of 2. So that says that the kinetic is equal to the potential, okay, when it's at x max over the square root of 2. Okay, and on your calculator, you remember that number from trig class, 1 over the square root of 2 is about 0.707, all right? So the kinetic and potential are 50-50 split, not at the halfway point, but about 70.1%, okay? It's nonlinear, right? That goes to sine squared and cosine squared. Okay, so the kinetic and potential are equal at about 0.707 x max, all right? Now, I think there's a homework problem where it asks you to do this as well, okay? Easier way to do this, because I want to look at this, I want to look at the curves, okay? But the easiest way to do this, where's the kinetic equal to the potential? Okay, you write down the total energy, okay? You're trying to find where k is equal to u, all right? Well, if k is equal to u, then right here you're going to set k is equal to u, okay? So instead of k, now I have u. So u plus u is 2u, okay? So the total energy is 1/2 kx max squared. Potential energy is 1/2 k times the x value squared, okay? Get rid of the halves, get rid of the k, solve this for x, okay? Solve it for x, and I get the exact same thing, okay? That the potential is equal to the kinetic at x max over the square root of 2. All right, so in chapter 2, when we had a car, okay, going down the road, okay, equation 1 allowed us to find how fast it was going at a certain time. That was for constant acceleration, okay? Well, we found for simple harmonic oscillator that the velocity, think about equation number 1 equivalent, okay, goes as sine omega t, okay? It's sinusoidal. The acceleration is not constant. Okay, so think of this plays a role of equation number 1 for simple harmonic motion now, All right. And then in chapter 2, we used equation number 3 here. Okay. This tells you how fast the car is going at a certain place. Okay. Remember, that only works for constant acceleration. Okay. Well, we want to find a similar expression for simple harmonic motion. Okay. Remember, we want to eliminate the time. We don't want to have to find the time first, right? Okay. So remember, this expression eliminated the step in finding the time. Okay. So we want to find a similar expression where we don't have to find the time when it's at that place. We just want to know how fast it's going. All right. So I'm going to start with total energy is kinetic plus potential. Solve it for kinetic. Okay. All right. And so I put in with total energy 1/2 kx max squared, potential energy 1/2 kx squared. All right. And then the kinetic energy is 1/2 mv squared. Got rid of the halves. Okay. Divide it by m. So the m came down on the bottom. Right there, all right? But remember, in this chapter, omega squared is k over m. So that stuff right there is omega squared, okay? And then just take the square root of both sides. So that kind of reminds you of equation number 3 in a sense that it gives you the velocity as a function of x, okay? So we've eliminated the step of finding the time, all right? So we can use this to figure out where's the velocity 0. Okay, well, velocity is 0 when that quantity is 0. Okay, so if you set that quantity equal to 0, okay, just bring that over. That says that velocity is 0 when x is equal to plus or minus x max. Okay, so that's at the amplitudes, that's at the ends. Okay, so we already knew that, right? The velocity is 0 at the end points. Okay, now we can also use this expression to figure out where's the velocity maximum. Okay, so you got to think, how do you find the value of x that maximizes that function? Okay, so you don't even need to take the derivative and set it equal to 0. Okay, so this is the velocity, and you're subtracting away x. So the velocity is the biggest when you're subtracting away 0. So Vmax occurs when x is equal to 0. Okay, and you know at x equals 0, okay, then Vmax is plus or minus omega x max. All right, so this expression comes in handy. I'll clean up a little bit. So that expression comes in handy because it allows you to find how fast something's going without first solving for the time it takes to get to that point.